full rigid body. A rigid body can have three different types of motion. Number one, PTM. This is called pure translational motion. Number two, PRM. This is called pure rotational motion. Number three, combination of PTM and PRM. This is called planar motion. This block is going down the inclined plane. These 2 points on this block moving with the same velocity v. This is also v. This is an example of PTM, pure translational motion. What happens here? Number one, we are discussing in PTM, every particle moves with same velocity. This is called PTM. Okay? Every particle moves with same velocity. This can happen on horizontal surface also. This block is moving on horizontal surface. The velocity of every point on it will have the same value. Then this is pure translational motion. This is on horizontal surface, every point moving with the same velocity. This is on inclined surface, every point moving with the same velocity. This is pure translational motion. Any kind of rigid body, if all points move with the same velocity, then this is called PTM. Okay? What happens in PRM? Here, every particle rotates with the same angular velocity about an axis of rotation. Every particle rotates with the same angular velocity about an axis of rotation. There are various types. We will be discussing only where it has motion, all particles have the same angular velocity about a fixed axis of rotation. Now, just let me explain one situation here. Suppose this is the axis of rotation, xy, and the rigid body is like this, situated here. This rigid body performs pure rotational motion about this axis. It means every point on it will have the same angular velocity, which is angular velocity of the whole rigid body. Let me explain what is a rigid body first. This is M1, mass M2, angular velocity of M1 is omega, M2 is also omega. And one very interesting thing to note that about the axis of rotation, they are in circular path. Every particle about the axis of rotation, they describe a circular path. But the simplest diagram I can represent here may be like this. XY the axis of rotation, and this is the rigid body. Okay? Axis of rotation I kept fixed here only. This is a particle describing circular path because the whole rigid body rotating about this axis of rotation. Angular velocity of particle P1 coincides with angular velocity of particle P2, and that will be omega. And another very interesting thing to note that rigid body, the way you take, no problem, but the center of their circular path will lie on the axis of rotation. Center of the circular path will lie on the axis of rotation. Okay? And this is pure rotational motion. Clear? Every particle rotates with. The third type of motion going to be combined motion, that is planar motion. Combined motion. What happens here? The combined motion, suppose an object on the horizontal surface is rolling. This object may be cylinder, maybe disc, maybe whatever. It is rolling. Rolling means the center of mass moving with the velocity in such a way that every point has the same linear velocity v, but it has another kind of motion also. It is rotating also. Okay, so this particle will have a backward motion. This one has a motion like this. This one has a motion like this because of angular motion. So this is something different. Here it is combined motion. Why? Because every particle have pure translational motion, motion with the velocity of center of mass, then pure rotational motion. Every particle has the motion about a fixed axis or a point. But today we will restrict our study about fixed axis. Okay? Now, that angular velocity, how are you going to define here? I am telling you. Angular velocity of a rigid body. How to define it? Suppose this is our axis of rotation and rigid body is here. This is the rigid body. What is rigid body? Rigid body, a rigid body is that which can't be deformed. What does it mean? Suppose there is a rigid body like this. There are 2 points on it, A and B. There is a fixed distance between them. By applying an external force, this distance cannot be changed. Okay? So in a rigid body, distance between two points can't be changed by applying a deforming force. Okay? Distance between two particles cannot be changed by applying a deforming force. This rigid body, angular velocity, how do you define? You take two particles here, or one particle only, this particle. You know, it will describe a circular path whose plane of rotation, this is the plane of rotation. Plane of rotation is perpendicular to the axis of rotation. Suppose this particle P goes from P to P dash by describing an angle delta theta. This angle be delta theta and time delta t. Then we define average angular velocity the way we have done it for circular motion. Average angular velocity delta, you can write omega only. Okay, that is delta theta by delta t. Now when delta t tending to 0, limit delta t tending to 0, delta theta by delta t or d theta by dt, this is called omega. And this is the angular velocity of all the particles. Particle here, particle any point about the axis of rotation, describing circular path, center lies here. This one has angular velocity omega. This has angular velocity omega. Rigid body describing a rotational motion with angular velocity omega. Unit of omega will be rad per second or revolution per minute. 1 revolution per minute, you know, 2 pi by 60 rad per second. You must have done it in circular motion. The only thing is that circular motion we have considered in terms of one particle describing circular motion. Here the whole rigid body, which is made of many constituent particles describing circular motion. Angular velocity has this expression, but this angular velocity should have a direction which is not like rotation 1. The rotation direction I have given omega means omega not directed that way. omega always will be directed along the axis of rotation. Omega is a vector directed along the axis of rotation. Okay, omega will be directed, this is the direction of omega. It is rotating with angular velocity omega shown. I have taken omega along axis of rotation. How to get it? Along this circle or along this, you fix up the fingers of your right hand. Curl the fingers of your right hand in this direction. Then the direction of thumb will give you the direction of omega. Okay? So direction of omega, how to get? Direction of omega will be the thumb. If you fix up your fingers of right hand along the direction of circle, then omega will be directed this manner. Okay? Now for this motion, if we take a point P here, O here, about which this has position vector r and PM is the perpendicular or PC is the perpendicular here. Center of circular path which lies on the axis of rotation. If we try to find omega cross r, then what do I get? Before that, I'd like to tell you one thing. I have told you V will be directed, I haven't told you today, I told you earlier, V will be directed in tangential direction. In any circular path, V directed tangential, always. Now, if we try to find omega cross r, what do you get? See, this is our r. It will be omega cross OP. You can see the diagram. By vector, it is OC plus CP. So, omega cross OC plus omega cross CP. Omega cross OC will be 0. Here omega cross OC equal to 0 as they have the same direction. So this will be omega cross CP. So omega cross R is coming to be omega cross CP. CP stands for what? This C to P, you take R perpendicular. Perpendicular distance from axis of rotation. Then what do you get? Omega cross R, that is going to be omega cross R perpendicular. Okay? Now omega along axis of rotation. R perpendicular is radially outward direction. If I take the circle here, for your better understanding, taking the circle here, we have taken omega in this direction and R is in this direction, R perpendicular in this direction. Then if you take omega cross R, curl the fingers of right hand from omega to R, then V is tangential. And in a circular path, V is always tangential. So have you done any mistake by taking omega along the axis of rotation? No. Omega has to be directed along axis of rotation always, because This is describing a circular path, and in circular path, velocity is tangential direction. So by convention, if you have taken omega along axis of rotation, this is justified. Direction of omega is justified as V is tangential. Am I clear? So direction of omega, whatever I told you, that will be in accordance with the circular motion. Now we are in a position to define angular acceleration, alpha. What is that? Because omega exists, its rate of change must exist. So alpha will be d omega by dt. Direction of alpha and omega is the same. Okay? During PRM, the direction will not change. But you can bring the case of spinning top. Spinning top is not like that, but today's class I will not be discussing spinning top. In spinning top, both alpha and omega changes. Why? Because axis of rotation direction also changes. Top. Okay. Okay, we restrict our study till this only, where alpha and omega will remain the same. It will not change during the pure rotational motion. Okay. Now we are going to define torque acting on a rigid body. Torque acting on a Okay, before that, let us do torque acting on a particle. Or we can define this way, torque, moment of force. Let us do that first. Particle or rigid body definitely will come one by one. The torque due to a force or moment of force. What is that? Moment of force. See, you have seen that your door in your flat can be opened quickly, easily, if you apply force at one extremity. But if the force applied near the hinge, then movement will be difficult. Why? Because when you apply force near the hinge, that force has least effect. That is, rotational effect will be small. If you apply force at larger distance, then its effect will be more. That's why you can open it easily. Okay? If you imagine that we have applied a force at a point P on an object, any object, or at a point, there is objects here. You take an object, no problem. Just discussing single force here. At the point P, you have applied a force. Okay? You have applied a force here at the point P. This is the line of action of the force. We have applied force at the point P. Now, moment of the force about a point, about any point. We are taking a point O here. This is a point O. O to P, if you join, then O. Moment of force moment of force F about, we have applied force at P, about O is defined as R cross F. This is your R vector. R vector going this way, R cross F will indicate this one as tau. This is also a vector quantity. This is defined as cross product of two things, that R vector and F vector. Okay, this is torque vector. I just remind you one thing. If you have taken R equal to, say, that OP, we have taken I plus 2j minus k, and F vector we have taken as 2i plus j minus 3k. Then moment of the force will be what? R cross F. This cross product you know, I, j, k, and this is 1, 2 minus 1, 2, 1 minus 3. So this is going to be I multiplied by minus 6 plus 1 minus j into, this is minus 3 plus 2 by determinant. You know how to solve it, cross product, vectors you have done. So this is going to be minus 5i plus j minus 3k. I wanted to show you just to prove that this is also a vector quantity. And direction of tau will be, direction of tau can be determined by right hand thumb rule. In the same manner, curl the fingers of your right hand from R to F. Then R cross F will be perpendicular to plane of paper. And if the rigid body rotates, if the body rotates for this force or the particle rotates, then axis of rotation is perpendicular to the plane. So direction of tau must be along omega to rotate an object. Otherwise rotation will not be possible. Rotating means that axis of rotation perpendicular to plane, the way you have defined. So tau must be directed in that direction. So moment of force is R cross F and it produces rotational motion. Direction of tau will be along the direction of axis of rotation, then the rigid body rotates. If it is not in that direction, the rigid body will not rotate. I will explain with many examples to you, just do it. Now, this R cross F, if you take the magnitude, see what is going to happen. R cross F, I am simplifying it here. The tau, we got this thing, R cross F, this angle be theta. So mod tau will be what? Mod R cross F, that is RF sin theta n cap. RF sin theta is constant and mod n cap is 1. So tau equal to mod tau RF sin theta. Or you can write F into R sin theta. What is R sin theta here? From here if you draw a perpendicular, OM the perpendicular, this angle is also theta, this part is R, then this part is going to be R sin theta. Okay? So, torque is F into R perpendicular. This R perpendicular is OM. Its length is R sin theta. And by now, we will be referring OM as lever arm. Okay? This OM will be considered as lever arm. What is that? Lever arm plays a very important role to understand direction of torque. Direction of torque, how to find? It is clockwise, I mean effect. Effect of applying torque may be clockwise or anti-clockwise. How to decide torque result is clockwise rotation or anti-clockwise rotation? Very easy. In problem, everything will be cleared with many examples when you are solving problem, but here you must know the direction, then calculation will be easier. Imagine the force is not acting at P, force is acting on the lever arm. Okay? If force acts on the lever arm, you just imagine, and the lever arm rotates clockwise, then tau is clockwise. But if it rotates in anti-clockwise sense, which one rotates? The lever arm. Anti-clockwise sense, then the torque is anti-clockwise. So, when a body is subjected to many forces, what is the net torque acted on it and effect is clockwise or anti-clockwise, you will be finding it by remembering this principle. That lever arm you taking drawing perpendicular, whether the lever arm rotating clockwise or anti-clockwise, that you find, you imagine that force acting on lever arm only. Every time you have to draw the lever arm. If lever arm rotates clockwise, then it will be clockwise torque. If it rotates in anti-clockwise sense, then it will be anti-clockwise torque. Okay? Now we define angular momentum. What is that angular momentum? Suppose an object of mass m moving with velocity v, so that its momentum vector is p equal to mv. This is linear momentum. Its angular momentum about the point O, where OP equal to R. This is R. Angular momentum of a particle is defined as the moment of linear momentum, and we'll be denoting this one by L. What is that? R vector going this way, R vector. P vector is going this way. This angle be theta. This is the direction of R vector. L is defined as R cross P. L will be defined as R cross P. Again, you apply the cross product rule, you will get the value of R cross P. But if we take modulus, then mod L going to be mod R cross P. This will be what? Mod RP sin theta n cap. Modulus of n cap will be 1. So this is just RP sin theta. This is just P into R sin theta. R sin theta is what in this diagram? Again you produce this line of action backward. OM is the perpendicular. This is R perpendicular. This is theta. So R perpendicular equal to R sin theta. So L going to be equal to P into R perpendicular. Okay. So moment of linear momentum is momentum multiplied by R perpendicular. This is very easy to observe in circular motion. Okay. What do you observe in circular motion? In circular motion, this is the axis of rotation. Okay. Linear momentum is tangential m into v, and this is your R perpendicular. P vector this way. This is R. This is P. So R cross P this time going to be R perpendicular, same thing, into P sin 90 degree. If you take the radius as R only, that is R into MV. This is MVR. Okay. Now, on this R cross P, if you find the rate of change of angular momentum, will reach a very interesting result. All these quantities are connected. How? We discuss here. Rate of change of angular momentum. What is that? That we have AL equal to, for single particle, R cross P. This is for a particle. If we differentiate both sides, what will you get? dl by dt going to be ddt of R cross P. This is nothing but dr by dt cross P, derivative rule, product rule, R cross dp by dt. What is dr by dt? This is V, and P stands for what? mv. M into V, and dp by dt is what? Force. V and V have the same direction, their cross product will be 0. This will be R cross F. R cross F is what? This is tau. Therefore, dl by dt is equal to torque acting on the particle. So, rate of change of angular momentum is, this is for a particle, is equal to the torque acting on it. This is very important to remember. Therefore, rate of change of angular momentum of a particle equal to torque acted on it. Okay. Now for system of particles, how do you define angular momentum? This is for one particle you have done. For a system of particles, you have to, these are all vector quantities, not scalar quantities. So you have to find angular momentum of all particles. This is L1 vector plus L2 vector. Suppose the rigid body or any system, not rigid body, for system of particles, n particles are there. So L will be L1, the angular momentum of first, angular momentum of second, angular momentum of Nth. This is nothing but I equal to 1 to N Li. Isn't it? But Li is what? Li is, this is I equal to 1 to N Ri cross Pi. We are taking the ith particle, which is the representative of all the particles here. So L is going to be sigma Ri cross Pi. If we find the rate of change of L differentiating with respect to t, what do you get? dl by dt equal to d dt of sigma I equal to n Ri cross Pi. Clear? This is Li, no? So sigma I equal to 1 to n d dt of Ri cross Pi. And just we have seen that Ri cross Pi derivative result is tau. So for ith particle, this is going to be tau I. Since tau I equal to d dt of Ri cross Pi. Okay, so for system of particles, therefore for a system of particles, rate of change of angular momentum is equal to net external torque. It's okay? You can write net external torque. Will you say this one net external torque or just external? Just torque. I have not mentioned external torque so far. Just net torque acted on it. This torque may be internal, may be external. Okay? This torque may be internal, may be external. Now, if we write dl by dt expression, dl by dt if you want to write, then it was sigma, if I continue from there, I equal to 1 to n dl by dt. No, not from dl by dt. We start from tau only, net torque only. Okay? Net torque. We denote this one by tau net. Now tau net is equal to sigma tau I equal to 1 to n. Therefore, tau external is going to be tau net. Sorry, again I am doing the mistake. tau net, this is also a vector quantity, all are vector quantities, please remember that. Now tau net is going to be what? Ri cross Fi, I equal to 1 to n. This Fi is what? We can say internal, external, no problem. But Fi is not only internal, not only external. Now Fi is Fi internal plus Fi external. Okay, you can write this way also, the way your textbook has written, Fi internal plus Fi external. So if you write here, it is going to be I equal to 1 to n Ri cross Fi internal plus Fi external. So tau external will be what? Sigma I equal to 1 to n Ri cross Fi internal, just open the bracket, I equal to 1 to n Ri cross Fi external. I am deriving not only because of your that important theory important for your school examination, very important topic, but to understand the matter, why everything will be replaced by external only, why this thing is 0, because the torque due to all internal forces, because M1 on M2 the force F12, F21, F12, they are equal and opposite, they get cancelled. So all these internal torque in our calculation, all internal torque or all torques due to internal forces gets cancelled. Okay, so this part going to be 0. Therefore, tau external will be sigma. This net I am replacing by, it was still this is tau net. But tau net reduced to what? I equal to 1 to n Ri cross Fi external. This will be tau external. Okay. So tau external going to be Ri cross Fi external, and this thing is actually dl by dt. We have started from there only. We have calculated dl by dt here. We have started from there. We found dl by dt tau net. Now we have got that tau external, tau net is tau external, so we can write this. Tau external equal to dl by dt. This is a very important topic to discuss. Okay, this is such a topic with which you can explain Kepler's laws of planetary motion also. Okay, there is no other direct proof. From here you can get it directly. Now, on a rigid body, if tau external, system of particles may be reduced to that rigid body. Now, if tau external is dl by dt, now assume that for system of particles, let me define first. If tau external 0 then dl by dt equal to 0. Therefore, L equal to a constant. Okay. So, this is principle of conservation of angular momentum. What is that? That is, in absence of any external torque, angular momentum of a system of particles is conserved. Got it? In absence of any external torque, the angular momentum of system of particles remain conserved. Clear? So far we have related that, see, the rigid body is also system of particles. We will extend this concept for rigid body also, no problem over there. Tau external dl by dt, if you write there. Now, after getting this kind of relations, we have to think about equilibrium of rigid bodies. I am telling you theory now. When we will solve problem one by one, all these will be very clear to you. Just keep all these concepts in your mind. Many good problems are there. Equilibrium of a rigid body, okay. So rigid body equilibrium means it doesn't have any accelerated motion, no accelerated motion. Equilibrium means that with uniform velocity it can go, but no accelerated motion. And number two, or you can see that that pure translational motion due to a force will not be there. No accelerated motion, no rotational motion. But first one implies what? Sigma Fi will be 0. Assume that it consists of n particles, sigma Fi 0. It has three components, Fix along x-axis will be 0, then Fiy along y-axis it will be 0, and Fij also will be equal to 0. And no torque, no rotational motion 0 means torque will be in rotational motion. No other factor is there. Here in rotational mechanics, we will consider the effect of force as torque only. So everything will state in terms of torque. No rotational motion means tau net will be 0. That means tau external along x-axis. Tau net is tau external only. This implies tau external equal to 0. So this is tau external along x-axis 0, tau external along y-axis will be 0, and tau external along z axis also going to be 0. Okay. So you calculate net torque, that will be 0. You calculate net force, that also will be 0. Okay. We will solve lots of problems. You have to wait for the next session. Now we are going to define couple. What is that? Couple is, suppose you want to open the lid of a bottle. What do you do here? If you want to open the lid of bottle, you have to apply force in one direction. No, you have to apply force this way and this way. You have to bring rotational motion, then only it will open. No, if you are applying here, if you are applying here, these two equal and opposite forces, you will say that why equal? If you don't apply equal and opposite, then what will happen? If you don't apply equal and opposite, then it will have accelerated motion. So we need couple. Couple means two equal and opposite forces constitute a couple. Two equal and opposite forces constitute a couple. Okay, this couple had some effect that is measured by moment of couple or torque. What is that? Moment of couple. We imagine that these two forces are acting this manner. One this way, the other one this way. Okay? This is the axis of the couple. One force F acting here, one force acting here. Let D be the distance between two forces. Okay? How to find moment of couple? Moment of couple, for finding it, you need to take a point on the axis. This point be O, whose distance from this end is x. Distance from other end will be d minus x. Okay? So moment of couple is going to be what? Moment of couple is equal to this F into D. This will rotate the lever arm. This is a lever arm in clockwise sense. So this is clockwise, and this one also will rotate in clockwise sense. Plus F into, this is F into X plus F into D minus X. So if we add these two get cancelled, it is going to be F into D. Therefore, moment of couple is equal to either force multiplied by distance of separation. So it is irrespective of the point. Wherever you take, then it will be the same. Now imagine there is a lever. Okay? Lever has many examples in nature. I am taking just this one. Lever. a lever will be pivoted at a point, maybe seesaw, maybe straight bar, whatever. Okay? This lever will be in equilibrium. Under what condition this will be in equilibrium? If we apply a load at one end, then we have to apply force at the other end to keep it in equilibrium. This point we are balancing. This is the balance point. And suppose there is a load here at this end, which is F1 is actually weight of some object, and you have applied another force F2 here, and this is the point about which you are balancing. Okay? Then if this is the balance point, a reaction upward will be equal to force acting downward. This is the balance point. This is a balance. This O is the balance point. O is the balance point. R equal to F1, F2. And to maintain the equilibrium in the lever, for the equilibrium of the lever, you can say net clockwise moment tau clockwise equal to tau anti-clockwise. Tau clockwise is what? This length be d1, this is d2. There it will be f1 into d1, f2 into d2. Okay? That clockwise torque for equilibrium, clockwise torque must be equal to anti-clockwise torque. This is called principle of moment. Principle of moment. It states that tau clockwise equal to tau anti-clockwise. So F1 d1 is equal to F2 d2. Therefore, F1 by F2, F1 by F2 is going to be what? d2 by d1. This is principle of moment here. Okay? And mechanical advantage of the lever, is F1 by F2, which is given by d2 by d1. Okay? So principle of moment done. Now we will do CG, center of gravity. Very easy to understand. On an object or a rigid body, whatever there, it is made of many masses, their weight acting vertically downward. Okay? The point about through which you can balance it, that is called center of gravity. Okay? This R through which it will act, it is called center of gravity. And the torque of all the weights about O, you have applied the force at O, say, about O must be 0. So, how do you define center of gravity? Rigid body or any object is made of many masses, their weights acting vertically downward. You determine a point through which you can balance, or through which the resultant weight will act. Then this will be the center of gravity through which it will act, that is called center of gravity. Okay? Now, if we consider dynamics of rotational motion, we have to pay attention in the equations of motion. That is, for a rigid body, these equations are valid. Omega square equal to omega 0 square plus 2 alpha theta, and then theta equal to omega 0 t plus half alpha t square. What omega 0 stands for? It is something like the initial velocity in speed velocity what you have done there before. In angular motion, omega 0 plays the same role as that of u. Alpha stands for what? Angular acceleration. And theta is what? Because in rotational motion, this is called angular displacement. Okay, so all these equations are similar to that before. What you will do there at home, you will find these equations derivation. You will start with omega equal to d theta by dt. Okay, from there, and alpha equal to d omega by dt, you can derive all the equations one by one. You will derive, and just giving you the clue, d omega by d theta by dt. Similar to that you have done in case of accelerated motion in kinematics. Use this to get this equation. Okay, and use this twice to get this equation. Use this once to get this one. This is the clue from my side. Another thing is there, that is, what is the work done to rotate a rigid body? Work done to rotate a rigid body. This is given by, on a rigid body you have applied a torque tau, you have rotated by an angle d theta, then the work done is given by dw equal to tau into d theta. No vector is required, just tau into d theta. Very easy to derive. You can take any rigid body here. Okay, it is rotating by some arrangement, rotated by an angle theta over there, so that the force applied was F, this distance is R, and if it rotates by an angle delta theta, then this linear displacement ds will be equal to r into delta theta. So work done will be F into ds, that is F into r into delta theta. But F into r is what? Tau. So work done will be tau delta theta. You can write delta w equal to, or dw equal to tau into d theta. Work done to rotate a rigid body. And next we will do angular momentum of a rigid body. For a rigid body, you can show that L equal to I omega and torque tau equal to I alpha. Alpha is a vector continuum along omega. Tau is I alpha and L is I omega. And again, if you differentiate this will be dl by dt I d omega by dt I alpha, and this will be tau external. But the question is how to get it. Moment of inertia you have already done. I am just showing you by taking a rigid body here. Okay, how to get L equal to I omega. Already we have defined for single particle. This has mass m1, m2, mn, and this is an arbitrary mass mi at a distance ri, rotating with angular velocity omega. This is r1, r2, rn. What is the linear velocity here? r1 omega. Okay, what is the linear velocity here? r2 omega. The same manner here. So A will be what? mv1 into r1. What is v1? Omega r1 into r1. If you take it for ith particle, mvi into ri. So Li going to be what? m omega ri square. Okay? So A will be what? Net angular momentum sigma mi, sorry, this is mi omega ri square. So this will be sigma mi ri square omega. So L going to be I omega. For a rigid body, L is I omega. For a rigid body, for any rigid body. Now differentiating with respect to T, what do you get? dl by dt will be I d omega by dt. So dl by dt equal to I alpha, because d omega by dt is alpha. But I alpha is tau external. Therefore, dl by dt equal to tau external. Now, if tau external 0, then dl by dt equal to 0. So, L equal to a constant, that is I into omega equal to a constant. Okay. So, moment of inertia and angular velocity product will remain constant. This is principle of conservation of angular momentum for a rigid body. At any instant, if it is I1 and omega 1 angular velocity, next instant, in absence of external torque, it is I2 and omega 2, then these two must be equal. Maybe another situation is changed to I3, omega 3. They all must be equal. Okay? That's all about the theory portion. You have done center of mass, you have done moment of inertia, you have done rotational motion basics. But each and every topic I have discussed in this session needed to be clarified with lots of numerical. Wait for the next very interesting session. I will be discussing all these one by one, and I will dragging the concepts we have developed here. Okay?